going to see the continuation of global optimization technique and which is Markov random field. I'd like to summarize the previous regularization technique. In previous regularization technique, our goal is to identify the minimum energy function E equal to E data term plus lambda into ES. ED is data term, ES is smooth term, and we have seen both in continuous domain as well as in discrete domain. In continuous domain, we'll take integration. In discrete domain, we'll take summation, and we will have formula for ED. Here we will have formula for ED, and this is for data term. In case of smoothness term, we have one dimensional as well as two dimensional. So this two dimensional formula is preferable for image, and in 1D as well as in 2D we have first order derivative, and that is represented as E1. Here we know we have second order derivative, that is E2. Second order derivative is better, produce better result in smoothness. Here also I have first order derivative. Here also we have second order derivative. The same is applicable for discrete domains also. Here we'll see all the formulas in integration. Here we'll see all the formulas in summation. Smoothness also we have first order derivative as well as second order derivative. Second order derivative is preferable for good smoothness. So and so formulas were seen in the previous regularization video. Now we are going to continue the Markov random field. So regularization will minimize the energy function that is completely based on data and smoothness. In Bayesian model, we'll see the probabilistic alternative. So one such method used is Markov random field. So Bayesian rule, we know the Bayesian theorem. Give me a minute. So Bayesian rule, we know Bayesian theorem is P of x given y equal to P of y given x into P of x divided by P of y. So posterior equal to likelihood into PR divided by normalization constant. We can simply omit the normalization constant. So the remaining term would be P of x given y equal to P of y given x into P of x. We can take the negative log on both sides. So which results in minus P of x into y, x given y equal to minus P of y given x minus log P plus C. This is represented as energy function. So minus P of minus log P of y by x is likelihood, and minus log P of x is the prior. So we need to minimize the energy function. So the last term is written as R min of x. We are going to find the minimum one, and now we are focusing on discrete results only. So discrete results means all the data are represented as a separate pixel. Let me show you one example. You might understand this better. So here I'm showing a original penguin image. So original image is having a good adjacent features. The second one is denoise one, image corrected by noise one, by a noise with missing data. Black bar, it has to be refilled with the original data, and the background is somewhat blurry. So I'm going to restore it to the original image, that is known as image restoration, and this black bar is filled with some pixels. So this is my predicted one. I'm giving the noisy image, and I'm restoring it to the original one. So this is my output, and this is my original one, or considered as a input. Okay. So on denoising, I'm getting some result. I need to compare the restored one with the original one to identify how good the result is. Okay, we need to determine the smoothness also, as well as we need to determine how exactly the missed data is matched. This black bar, how good it is matched. So this is known as output or predicted one. Now see this. I'm going to consider the set of input pixels as D, that is D represents original one, and the set of output pixels F represents the restored one. So I'm going to represent the data D as well as F. So D represents original, F represents restored one. I can identify the difference between F and D to determine the closeness of the restored image. So look at this graph now. F of ij, that is the data to be predicted or unknown, the data bar, black data bar we had, right? So unknown data, the white circles are unknowns. They are f of ij, f of I plus 1, f of j plus 1. So if you take a point in a graph, okay, x comma y means on x axis x will be incremented, on y axis y will be incremented. So the next neighbor would be 0, 1, 2 plus 1, right? So 0, 1, 2, 3, so on. So I'm going to take a pixel ij. So the next neighbor would be I plus 1 and j. On vertical, the next neighbor would be I comma j plus 1. So this point would be I plus 1 j. So these are the missing data I want to predict. And d is the already known value. The nearby pixel may have known value. So in case of penguin, the data bar is missing value. So the next pixels are the known one, right? The nearby pixels are known one. So that is d of ij. Wij represents weight, sx and sy represents the adjacent pixels. So if you focus on n4 neighbor, I won't focus on diagonal. And if you focus on n8 neighborhood, I'll take 8 neighbors. I'll consider the diagonal neighbors also. So Sx and Sy represents interaction potential and W represents the weight, also known as penalty. Now we are going to consider the term energy equal to Ed plus Ep. So instead of Es, we are going to consider the prior. Okay, prior is similar to smoothness term in regularization, and Ed represents data term. It is used to find how good the observed data is. And Ep of X, we are going to find the prior energy. The prior energy is depends on the neighboring pixels. So if I'm going to take one pixel, I have to consider the pixel neighbor pixels. So I and j, k and l are neighboring pixels. So we are representing I comma j, k comma l belongs to neighbor, and we represent compatibility function of all the neighboring pixels. And three types of Markov random field are going to be considered. One is binary, another one is ordinal, another one is unordered or unordinal. Binary will focus on 0 and 1. Ordinal will follow some numerical order, will have certain order. In unordered, no order will be followed or no labels will be defined. So if you are processing a image, so if the image is child, I can order a adult, child and senior. So this is we are following certain order, right? After child will become an adult, after adult will become a senior. So some kind of order can be followed in ordinal image. In case of unordered, we can say the example as sky, terrain. So no order can be followed. Okay, so if you want to process only two values, then we can go with binary MRF, and it can take only the values zeros and one. The term ED is represented as W of delta, F of ij and D of ij. I said earlier D and F represents the original as well as restored image. I am going to measure how good the data fit is. So D represents the original penguin image or whatever may be, and F is the restored or the predicted one. And this term, if both the term predicted as well as original is equal, I can say 0. If they are not equal, I can say 1. I'll focus on both the data. In case of smoothness, I won't focus on the original data. You see the formula here, no D term is involved, only F term is involved, because I'm focusing on smoothness of the predicted one only. I'm not bothering about the smoothness of the original one. Okay, so only the predicted one is considered. So I'm going to take Sx as well as Sy. So both horizontal and vertical smoothness has to be considered. So Sx delta f of I comma j. In case of horizontal, only the I will value will be changed. So f of I plus 1. In case of vertical, I will be remaining constant, j will be changed. So ex plus ey, we need to find the compatibility like f of ij and f of I plus 1 comma j, and f of ij and I comma j plus 1. And the ordinal valued MRF will follow the natural ordering. we may use it to identify the depth level of the images. And here the data term is, instead of values zeros and one, will identify the differences. Based on the difference, we can follow certain orders. So I have to find the difference here. Previously, we won't find any difference. We'll just compare. If they are same, we'll assign certain value. If they are different, we'll assign certain value. Here, the difference is that we will do the subtraction. And in unordered labels, we will provide a label to the function. So the f is changed to l represents label. We are labeling it because no numerical ordering is followed here. So based on the label, I can check the compatibility. If the label is sky, both the labels identified, original is sky as well as the restored one is also sky, I can say it is okay. So I am changing the function f into the labels. So L represents the label, V represents the compatibility function, how good the labels are. So in XX I'll compare I plus 1 and j. In SY I'll compare I comma j plus 1. So this is about unordered labels in MRF. And see this image. I already told A represents original image, B represents the corrupted image, and C and D are image restored, but it is using loopy belief propagation and it is using graph cuts. Both are two separate optimization technique. Loopy belief propagation means, so all the black bars or missed ones are updated with the communication based on the neighboring pixels. So this pixel, this is the missed one, right? So this pixel will communicate with the neighbors and update its value. This pixel will communicate with the neighbors. Based on that, the opted value is filled. In case of graph cuts, I'll represent all the images of image pixels as a nodes. So the foreground image is represented with source node. The foreground image and its neighbors are connected with source node, and the background image is represented with sync node. So background image and its neighboring pixels are connected with sync node. If I want to separate foreground and background, I can simply disconnect the edges that are connected with source node as well as sync node. This may result in a separation of images into foreground as well as background. So based on this concept, I can restore my image, that is known as graph cut. And these are the techniques discussed here. Some other optimization techniques, right? So local greedy method means it will look only for the current best choice. If the next move is good, then I can take it. So I may get stuck in local maxima also. There may be a global best solution. So I focus on immediate success only. Some kinds of method or gradient design, contextual classification, iterated condition modes, and highest confidence first. So these are the local greedy approaches. Stochastic methods, I'll focus on randomness. I may not focus whether the result will be best or not. I'll just move to the random value. Simulated annealing is also one of the concept comes under concept of metallurgy. It may jump out of local minimum, and it is one of the optimization approach. Graph cut, so the nodes are represented as a pixels and the edges are represented as a relationship, and I can cut the source node nodes as well as the sync node connected nodes. That results in image segmentation. And I can also say I want to find in a minimum cost, so the minimum cut will be the lowest energy. Then belief propagation, and it is based on iteratively passing messages between the neighbors. And dynamic programming is good for one-dimensional problem, but it is not scalable for general 2D grids due to its complexity. And then next one is multi-level graph optimization. So this is the initial labeling. This image is having alpha, beta, and gamma. Alpha is represented in red, beta is represented in green, Cyan is represented in magenta color. I want to fill the uneven pores into red, green, or cyan based on the nearby pixel. This is the initial labeling. In standard move, I can change only one. I could see changing only one pixel, that is highlighted in yeah, white color circle. The only empty pore is blocked or The next one is alpha beta swap. In alpha beta swap, I can take a pixel in the alpha region as well as I'll take a pixel in beta region and I'll swap both the values. That is results in alpha beta cores are completed and the gamma side values are still empty. In case of alpha expansion, I won't take two pixels. I'll take only the alpha pixel. Either I'll keep it safe or I'll change it to some other color. So in this case, I can get a complete graph that is known as multi-valued MRF. Swap moves and expansion moves. The C represents swap moves and D represents the image D represents alpha expansion moves. So that is multi-valued MRF. Swap moves will iteratively exchange the labels between pair of pixels. In case of expansion moves, it iteratively allows a group of pixels to switch to a single label that reduces the energy. So as a summary, we have seen Markov random field. Here we are going to consider the energy term as E equal to ED plus EP. ED represents E data and EP represents E prior, and we have seen three types: ordinal, binary, and unordered. We have to focus on the original data as well as predicted data, both D and F in case of data term. In case of smoothness term, we'll focus only on the predicted F and we'll focus on the neighboring term. And we have seen the formulas for that, and we see some other optimization technique to perform the image restoration of the penguin. And in multi-valued graph, we can perform either swap moves or expansion moves to perform image analysis. Thank you.